Okay, thank you. Good afternoon to everybody. I hope that we will have a chance to wake up you after lunch. Therefore, we will talk together today. That it will be much more interactive, and we expect a lot of questions because the most important part of this conference is for sure discussion. It's not talk itself. So please ask and prepare all the questions. We'll be happy to discuss. I would like to start with the question which was already addressed by Andreas, that for sure Lustre is well known for HPC market for a long period of time, but does AI workload change everything? Or AI workload doesn't change anything for Lustre installations? And it's not a real question, by the way, and I would like to start answering on this question, not using our own specific answer, but to refer to the discussions that we have at the previous user group. It was LAC at Texas this year, and let's look at the slides that was presented by Aurelian from NVIDIA. And by the way, all this presentation as well available on LAC24 website, and I strongly recommend to look at this presentation to everybody who has no chance to do it before. So, what is more or less objective part of workload for the storage for AI. Everybody talked about checkpoints, that sequential write is matter. And for today workloads, sequential write means not only gigabytes per second and not only dozens gigabytes per second. It could be for some installation hundreds gigabytes per second and even terabytes per second. And it's more or less what everybody talking about. But is it all? Not so, because as well, random read is a pattern that could be significantly considered for AI workloads, because random read is very important pattern for uploading server to the GPUs in case when model start to be calculated on GPU cluster. So basically it's not story only about checkpoints, it's as well story about random reads. And again, guys, I would like to refer that this slide is used by us from NVIDIA presentation from LAC. The whole presentation is available on LAC website. So, to be more detailed, as I told, read operations for random read matters as well. But is it all that matters for current AI workloads? Because when we are talking about 100 gigabytes per second, and when we are talking about million IOPS, then as well storage media is extremely important. And not all the tasks could be solved on traditional media for HPC, what relates to the HDD. A lot of attention relates to the NVMe type storages, and it's as well more or less a general point discussed at the present moment in every conference, but everybody. But what is important for NVMe? For sure, data integrity important for all storages, all workloads. And what we are doing, basically, the main Xenor product, the main Xenor idea is to provide reliable NVMe storage which support any type of RAID redundancy, even support redundancy N plus M when you could use M drives for the parity. And in case you have poor data integrity that doesn't provide possibility to use all the NVMe capabilities, then you don't have a great solution for storage at all. So let's, Daniel, help me and describe a bit more what we provide as a data resilience solution in our product.
Sure, Dmitry, I will help you. Well, our company the main focus of our company work is to build different RAID engines of different kinds. For now, our main products are two products, Z-RAID Classic, which we will talk today, and Z-RAID Opus. The main difference between them is that Z-RAID Classic is a classical Linux kernel-based RAID engine, which is optimized to build classical RAIDs from NVMe drives. Z-RAID Opus, if maybe you will be interested, is based on SPDK. It is a user space RAID engine, which allows us to get much more performance, much less latency. But the main problem with him for now is that in comparison with Z-RAID Classic, it cannot provide you a local block device, because a local block device should be created by a kernel driver. But Z-RAID Opus is located in user space. So today we will talk about Z-RAID Classic. Z-RAID Classic is a software-only RAID engine which consists of basically kernel module, the module which creates RAIDs, provides you access to the block devices, get access to the local block devices from which it organizes the RAID, and user space environment, which allows administrators to create RAID, administrate RAID, monitor their status, and so on and so on and so on. And all our slides today will include something about Z-RAID Classic. It is available as a standard Linux application, which is installed by standard Linux packages. It is available for most popular Linux distributions like Red Hat, Ubuntu, Alma, Rocky, Oracle, and so on. It is quite simple in its concept. It takes local drives, local block devices. We think that the best devices here are NVMe drives, but it theoretically can be also SAS SSDs and so on, and provides in response it creates a RAID or RAIDs from these devices and provides you a block device for each RAID, which can be used by you as any other block device in the Linux operating system. Let me check what we have. What is the next slide? Okay. Let me go back. Let me a little bit more information about. How can we go back? Yeah, thank you. A little bit more to our main technologies which we have in this RAID engine. Why this RAID engine? All our RAID engines are very fast because we have our own patented technology of checksum calculations. We are based on classical RAID, so we need checksum calculations, and we found how we can very fast and efficiently calculate the checksums. We use, in this product, we use AVX instructions, which firstly appeared in Intel CPUs for multimedia tasks, but they exist in this, basically they are an example of synced calculations, vector calculations. So we found a way, we found the formulas, mathematics, how we can calculate the checksums from the data on these instructions, and how we can recover the data in case, for example, of a drive failure. So this is one point, and another point is our data path, which allows you to utilize power of all the CPU cores if needed, even if you run a single threaded applications. If you will have more questions about our architecture, please ask after our presentation or in the breaks. I will be happy to provide you more details.
Okay, since Daniel, so let's discuss a bit more today about customer use cases, how our product could be integrated for real Lustre tasks. And let's start from one of the use cases that we have done with our partner out of Germany. In this case, it's Megware, and the customer is Friedrich Alexander University at Nuremberg. So what was the main customer challenge? First of all, they, as a lot of customers, use CEF as a storage for their tasks. And the main challenge for CEF was, as usual, performance. From one point of view, and the second topic, it's this, he has mentioned three-way CEF replication, but actually it's two-way replication. Every good presentation should have its own mistake. So in this case, it's two-way replication. And customer come to the partner, not to us, because we are working through our partners, and ask about alternative solutions that should be deployed in a short-term perspective. In this case, hardware environment was relatively simple, just 7 servers with 24 drives each. And what we propose? We propose architecture based on Lustre, not just we, but we with our partner, where every server we have 2 OSTs and 2 MDT. And in this case, in total, we have 14 MDTs and 14 OSTs with total capacity more than 700 terabytes. What we have done? We have just tested our solution in compare with CEF. The test was relatively simple. We use 4 servers for our solution and 3 servers for CEF. It's more or less the same. It's not exactly the same, but more or less the same. And what a partner could demonstrate to the customer as a result of this use case. For write test, we can achieve more than 60 gigabytes per second in compare with CEF 10 gigabytes per second, which is 6 times more. And in read, we achieved 80, which is 4 times more than CEF. But it's not only the case, because we do all this performance using parity RAID. It's just RAID 6. And in this case, you can use more than 700 terabytes capacity in compare with 400 that possible to use with CEF. And as well, you could use much more efficient network in our solution, which is impossible to use with CEF. The main question about this solution, actually, it was not a question for the customer. But in this case, customer was not interested in high availability because for this solution, it was not essential requirement for this cluster. But anyway, could we provide high availability as well in our solution? Should it be a disclaimer for further slides that Daniel would address in further part of the presentation. But prior we could go to high availability, let's discuss a bit more with partner testing, which is made on environment which was on a customer site just by case. So Daniel, let's do it again.
Yeah. Well, after this project, we had plans for one more project with the same partner. May I name the...
Yeah, sure.
We have a great partner in Germany named Megware, and after the project with the university, with FAU University, we had plans for some other project, but recently they came to us and said, guys, we just received a bunch of hardware, not for your project, for some other project, but we have time, and we would like to do some measurements just for us, because we want to understand if your solution really is so good, and we want to measure it and use use these numbers in our materials, internal materials. We said, yes, sure. We provided them the licenses for this hardware. And what hardware they had? They had 14 servers. Each server was equipped with 12 NVMe drives. The drives performance is listed here. They had quite fast network. Each server had 2 Connect X7 NDR cards, and each server was configured in the following way. They took 2 NVMEs for RAID 1, and this RAID device was used for MDT. And also they took other 10 drives and they formed RAID 6 with enough redundancy. And this device was used for OST. So the total available capacity of 14 servers was 388 terabyte. And they used 10 clients. The number of clients was taken especially to compare the results with IO 500 tests in IO 500 research 10 nodes category. Here is the scheme. Basically, I think all the scheme I just listed. So you see here 10 clients, InfiniBand network, InfiniBand cards, 14 servers, and rates on them. So here is some calculations of the theoretical performance. In case of multi-thread sequential workload multi-thread on NVMe, not on the hard drives, the total performance of multi-thread sequential reading is about, it should be about the total sum of all the drives performance. So the total drives performance for our case, for all our drives used in OST, is about 1 terabyte, a little bit less than 1 terabyte, 900 gigabytes per second. In case of multi-threading sequential write, the situation is a little bit different. In this case, we should take only 8 drives from each RAID. We have basically 10 drives RAIDs. So in this case, for reading, we take 10 drives performance. In case of writing, we take 8 drives performance, because for each writing, we have also to write 2 parities. So 2 drives are off. And the theoretical performance here is 431. So our client ran the test, IO 500 test from 10 clients, and basically on total score, he received the 3rd fastest Lustre-based result in the 10-node research category. If we will he also likes to experiment. He took another test program. He recommended also to use this program to me. I played a little bit, but to be honest, I think I've done something wrong. But during his tests, since this program, which is named LBench, allows also to specify the IO depth of writing, the results were even better. They were much closer to the theoretical performance on both reading and writing. So here is the theoretical performance and the real performance received with the LBench test. So the efficiency was about 90 or 80 or 90% for reading and 80% for writing.
Okay, guys, I see that we have just 1 minute to finish. So, related to the high availability, this disclaimer would be subject of the further discussion in this session, because up to now we don't have enough time to discuss it in details. But I would like to make only one point here, that we have joint solution with our friends from Western Digital, who would be deliver a talk tomorrow, and for sure they will be focused on this use case in much more details. It relates to the disaggregate storage based on their eBOFs. And the last point from me for today, we told a lot about sequential, but what about random? Related to the random read, I think that who is interested in this workload, please look at our presentation at LAC 24 this year, where we told about asynchronous random workloads there, and all the slides available, and it's in a strong compliance and totally in agreement with all the slides provided by Patrick about hybrid I/O, and as well what Andres referred today related to the hybrid I/O value for Lustre community. So that's it, and all your questions are very welcome after this session at any time today and tomorrow. Thanks so much.
Thank you. Any question? Yeah.
Could you elaborate more about the high availability technology, or using corrosing pacemaker?
Yes, sure. Well, in short, yes. So we saw that our retention, not only on Lustre tasks, but mostly on Lustre tasks, a project requires high availability. We know that Lustre high availability is the standard for standalone Lustre installations for high availability is pacemaker. So we just prepared the integration. We developed our own agent for integration of our RAIDs into a pacemaker cluster. And we also, a couple of days ago, we released, we support two configurations. We support SBB systems, and we already prepared basically a blueprint article about how to deploy Lustre on SBB system with all the details, because SBB system has its own limitations. Each NVMe is connected to each node only by 2 PCI lines. So to have better performance, it's better to split each NVMe into namespaces and create RAIDs from different namespaces on different nodes to utilize the full performance of the NVMe, and so on. And the second configuration which we support for now, it is the configuration which Dmitry mentioned, is configuration with eBOFs. One eBOF, multiple eBOFs, and so on. In this case, no need, I think, to create namespaces and do some other things. But here you have, here we have multipathing, and for now we support native multipathing, but native multipathing is the recommended multipathing method. It is recommended by Western Digital. So, yeah, two options here. For now, we support only dual-node configurations, but we have plans to support multi-node in the future.
Have you measured the performance of the failover? How long it takes for Lustre to?
For Lustre, yes. I'm not sure. I was not sure that my measurement was fully optimized, but the failover on SBB system, it took about, these numbers are in the article, not less than 2 minutes or about 2 minutes it took. More questions?
So
I still have...
For the recording.
Oh, yeah, okay.
So there are two components, that's my understanding here. One is the high availability, but the other one is the performance. And what kind of rate concept are you using? You know, what is basically hidden behind the curtain here?
A very classical rate, just rate 5 as it should be, rate 6 as it should be. So classical rate with distributed parity between the drives.
So it's standard rate,
yes,
right? There's nothing, you know, because originally this XI rate made me think there's...
It's a classical rate. So I think we can go back to the slide about our products. So sorry, I did not said what rate levels we support. We support rate 5, rate 6, rate 7.3, which means rate 6 plus 1 drive parity, rate N plus M, where you can select how many drives for parity should be used. With M more than 4, because if you take M less than 4, you will go to rate 5, rate 6, and rate 7. Rate 50, rate 60, rate 1, rate 10, and rate 70.
Yeah, and one should add related to this, we just released case study with NVIDIA where we had a chance to offload our rate on Bluefield 3, and in this case is working without any x86 instruction at all. And it's just used disaggregated drives all over the network, and all the rate calculations made on GPU itself. And it's thanks to our solution, it's just software, without no need to have any dedicated hardware as a part of the solution.
Question, how is the licensing? I guess you're paying for the license to use this Xen or X-Rate, right?
Oh yeah, the license model is very straightforward. I don't want to have a commercial presentation out of displays, but in any case, it could be basic license model. It's per drive. Yeah, and we can discuss in much more details how it could be done in a specific case.